Welcome to a brief introduction to the use of the Dean Stark apparatus in the organic chemistry lab. I'd like to begin by reminding you how common water is in the organic laboratory. Despite our best efforts to exclude it from many reaction setups, it's very difficult to get rid of all the water that's present in certain organic solvents and mixtures. Now, we want to get rid of all that water for a lot of reasons, one of which is shifting equilibria in favor of their products. For example, in the case of the condensation reaction of a Fischer esterification. We have an equilibrium here which is not particularly favorable, but removal of water can cause that equilibrium to shift, exploiting Le Chatelier's principle, until we have a nearly quantitative conversion of ester. Another example of when we might want to remove all the water from a sample would be in order to quantify the amount of water contained therein. So if we have a mixture of water and organic materials, and we have a technique which allows us to selectively transfer the water to another container, we can then measure the amount of water which was in the organic sample. These are just two examples of why we want to be able to isolate water from organics very quickly and efficiently. And one technique which is available for this is the Dean Stark apparatus. Shown here is one of the simplest Dean Stark apparatus you can build, designed to isolate an organic of lower density from water. The apparatus consists of a boiling flask attached to an inclined sidearm, which is then plumbed to a reflux condenser. Beneath the condenser is a region called the trap, which typically has a stopcock at the bottom so that the flow can be directed into a beaker or other suitable collecting flask. So now that you've had your tour of the Dean Stark apparatus, let's take a look at this thing in action. Let's begin by considering a very simple system with which we might use the Dean Stark. Naturally, water will be involved, with a boiling point of 100 degrees and a density of 1. Let's try to isolate this water from toluene, which boils at 110 degrees and has a density of 0.87. However, we need to acknowledge at this point that water and toluene, when boiled, form an azeotrope with a boiling point of about 84 degrees centigrade. And the composition of this azeotrope is somewhere in the neighborhood of 80% toluene. So let's see if we can separate the water from the toluene using our Dean Stark apparatus. I'll begin by charging the boiling flask with my mixture. Next, I'm going to plumb my cold water into the reflux condenser, creating a zone of cooling where vapor will begin to condense. As I apply heat to the system and my mixture begins to boil, we'll see that the vapor, this is the azeotropic vapor, reaches the reflux condenser, cools, and then falls downward into the trap. So this liquid is accumulating in the trap, but this is cold liquid, this is not boiling liquid. So our toluene and water will phase separate. As we continue to run the apparatus and the trap continues to fill, it will eventually reach a point at which it will be completely filled, and whichever liquid is on top, in this case the toluene, will begin to drain back into the boiling flask. If we continue this process, eventually the water, of course, would be expected to fill the trap completely. So to avoid this, we open the stopcock and drain some of the water which we've caught in the trap into a collection flask. When I do this, we can see how the Dean Stark apparatus truly works. It's directing the flow of water into a separate zone from that of the toluene. So at the end of my run, I can expect to have dry toluene in the boiling flask and pure water collecting in my receiving flask or my beaker. And this is the principle on which the Dean Stark apparatus works.